Alrighty. Howdy, folks. Let's look at section 7.4 in Laplace transforms chapter. Transforms of derivatives and integrals. DiffE theorem. Transform of a derivative. Laplace of f to the n of t. What in the world does f to the n of t mean? The nth derivative of f of t. Okay, so apparently the Laplace of the nth derivative of some f of t is s to the n, right? S is our variable, no surprises. N is known because we are talking about an nth derivative of f, times f of s, uppercase f of s. The reason you need, I'm kind of saying uppercase, is because in this particular part, you really ought to be able to distinguish your lowercase functions with uppercase f's. And the notation that we will use is, if a function is a function of t, variable t, I might say t for time, but that is not necessarily true. T is just another variable, but for the most part, for engineers, t will represent time because you're dealing with things like control systems where t represents time. Okay, so if I happen to say t for time, please bear with me. Okay, times f of s. We know what uppercase f of s is. It's the Laplace of f of t, right? Minus s to the n minus 1 times f of 0, lowercase f of 0. Any idea what lowercase f of 0 would represent? It's just a function's value, the low f of t, its value at t equal to 0, as simple as that. Similarly, there's an f prime of 0, so the first derivative's value of f evaluated at t equal to 0, and so on. And the very last term is minus f to the n minus 1, the derivative of 0. So the n minus 1, the derivative of f evaluated at t equal to 0. That's the last term. Cool. So could I ask you, based on that, can you figure out what Laplace of f prime of t ought to be? Right? Just using that theorem, would you be able to do it? Ask yourself, does it look like Laplace of f to the n of t? Yeah, n was nth derivative. What is n here in our case? 1. Yep, you're right. So what should the very first term be? S to the 1, right? S to the n, s to the 1 times f of s, that is s f of s. As simple as that. Cool, that is the first term. Let's also go ahead and figure out what the last term ought to be. Last term apparently needs to be f to the n minus 1 0, or evaluated at 0. So that is f to the 0 evaluated at 0. What do I mean by f to the 0? If f square or f prime is the first derivative, f to the 0th prime means take 0th derivative of f. That means do not take any derivative of f. So f itself evaluated at 0. Are you with me on this one? So the first term, when n equals 1, should be s times f of s, and the last term should be f of 0. Keep those in mind. Cool. Let's evaluate what the second term ought to be. There's a reason why I picked the last term to evaluate. So the second term would be s to the 1 minus 1, which is s to the 0, which is 1, provided s is not equal to 0, f of 0. So that means f of 0 is the second term. Wait a minute. First term, no dispute, s times f of s. Second term should be minus f of 0. What did we say the last term ought to be? F of 0. What? The second term is f of 0 and the last term should be f of 0. What does that mean? Oh, that means the second term itself is the last term. Isn't that cool? So think of it like that, and all of this will make perfect sense to you. So s times f of s minus f of 0. Cool. Let's figure out Laplace of f double prime of t. Now t is the n is equal to 2. Would you agree? First term, s square f of s. Yes, you're right. Last term, f to the 1 of 0. That means f prime of 0 should be the last term. Keep that in mind. The last term should be f prime of 0. Cool. So first time is s square f of s minus s to the n minus 1, s to the 2 minus 1 is s to the 1, f of 0. Second term is sf of 0 minus sf of 0. The third term is s to the 2 minus 2, which is 1, s to the 0, which is 1, f prime of 0. So the third term should be minus f prime of 0. Ring a bell? Yeah, the last term was f prime of 0. Oh, so that means the third term is the last term. You stop right there. So this gives us s square f of s minus sf of 0 minus f prime of 0. Cool. That's the way to figure the Laplaces of derivatives. Okay. And then the next thing we need to talk about is what's called convolution. Let's define convolution. If functions f and g are piecewise continuous on 0 to infinity, then the convolution of f and g, denoted by f convolved with g, that star you read it as f convolved with g, is the integral f convolved with g is equal to integral 0 to t f of tau g of t minus tau d tau. Okay, what f convolved with g is simply integral 0 to t f of tau g of t minus tau d tau. Okay, now this is a real big deal. I told you many times that Laplace transforms is something that you will use in control systems quite a bit. Specifically, it is this part that you use tremendously in Laplace transforms, this concept of convolution. There's a phrase which I will throw fairly soon called convolution in time domain is multiplication in S domain. I'll tell you what that means in just a second. So let's do a few things. One of the things we will cover first is to give you a conceptual idea of what this convolution is. How do you convolve two functions? Okay. And the second thing is we will observe this convolution in GeoGebra. And the third, why do we want to convolve, right? What's the purpose of this stupid convolution? There is a wonderful purpose for it. And finally, the Laplace transform of convolution itself. Okay. And first, how to convolve two functions? Let's take a simple problem. What's t convolved with t? Don't tell me t times t is t square, man. No. This is not a, it is a sort of a multiplication, but it's not quite. Okay. So t convolved with t. Well, could you apply that definition and be able to figure out t convolved with t? What is f of t here? T. What is g of t? T. Cool. So t convolved with t according to the definition should be a certain integral, right? What integral? Integral 0 to t of f of tau? What? Well, if f of t is t, what is f of tau equal to? Let me put it this way. If f of t equals t, what is f of 3? 3. F of 5, 5. So f of tau, tau. As simple as that. Cool. If g of t is equal to t, what is g of t minus tau? T minus tau. Oh. So, no big deal. This thing is fairly straightforward. You need to evaluate this particular definite integral 0 to t of tau times t minus tau d tau. That should be fairly straightforward, right? Yeah, it is in fact straightforward. Notice we are integrating with respect to the variable tau. So think of t as a constant. All right. And so t times the integral of tau is tau square over 2. So that's why I have t tau square over 2. Minus tau square, the integral would be tau cube over 3. And that's why I have tau cube over 3 here. Okay. All right. Now we need to evaluate that from 0 to t. That means wherever you see tau, replace that with a t to get the upper limit. And wherever you see tau, replace minus. Wherever you see tau, put a 0. So that gives you t cube over 2 minus t. That simplified becomes t cube over 6. Does it make sense? As simple as that. So this is how you can convolve two functions. Okay. Now, I'm going to show you this. I talked about observing convolution via GeoGebra. Let me take you there. Take a look at this. What we are trying to convolve is two functions. F of t is 2 and g of t is 3. Even though I say that, I should be a bit more precise. F of t is not 2 everywhere. Only on the interval 0 to 1, f of t is 2. Similarly, g of t has a value of 3 only on the interval 0 to 1. Everywhere else it is not defined as 0. Either way you can take it. So what in the world does convolution mean? Apparently that's equal to integral 0 to t of f of tau g of t minus tau d tau. What does that mean? Right? Now check this out. If f of t is 2, what would you say f of tau is? F of tau is also 2. Right? Same thing. So now think of this axis as tau axis, not as a t axis. Okay, the horizontal axis is tau. So we have f of tau is what you see here. G of tau is 3. That's what you see here. Okay, is this asking us to multiply f of tau and g of tau? No. It's asking us to multiply f of tau and g of something called t minus tau. What in the world does the graph of g of t minus tau look like? If g of tau looks like this, what does the graph of g of t minus tau look like? Now, for that, it depends on what the value of t is. Pay attention to that. The graph of g of t minus tau, how it looks, depends on what the value of t is. Now, I have a thing going on here, slider. T is right now 0. Okay? So, we have f of tau times g of negative tau. Do you know if g of tau looks like this, what the graph of g of negative tau would look like? Any thoughts? You remember back in pre-calculus or in high school, transformation of graphs you studied? G of negative tau is just a reflection of g of tau graph about the y-axis. You just reflect it about the y-axis. Okay. So for that, this is what I have done. Not only have I done a negative reflection, but also made a rectangle out of it. Okay. So this, just the top line itself, is g of 0 minus tau. Cool. Just the top line of this blue rectangle is g of 0 minus tau. Okay. Now we are getting somewhere. We apparently need to multiply f of tau, which is this guy. Let me make a rectangle even for that f. Okay, so this f of tau times g of 0 minus tau, which is this one. We need to multiply these two first, according to the inside stuff. But what in the world does integral 0 to t, what does that mean? That means we need to find the area under the product f of tau g of t minus tau between 0 and whatever the t value is. Between 0 and whatever the t value is. But t is 0 right now. Oh, okay. So look at the product of these two things and find the area under that, in the interval 0 to 0 of that product. Well, if you look at this, there is no overlap. So right now, the product of these two functions is just 0. Would you agree? There is no overlap. So this blue rectangle, the overlap part with the what's the brown rectangle, there is no overlap. So the product is 0 and the area under that is 0. Okay. Next, I'm going to move things. I'm going to increase t. Let's say I were to make t to be 0.1. Now, f of tau will not change. However, we have g of 0.1 minus tau. What does the graph of g of 0.1 minus tau look like if g of tau itself is just this horizontal line? The answer is this rectangle scooted to the right by 0.1 units. Let me repeat that. G of 0.1 minus tau is the blue rectangle shifted to the right by 0.1. Trust me on that. If you don't, this is how I want to argue. But I thought it was g of negative tau plus 0.1. When you add f of x plus a is a graph shifted to the left by a. Yeah. But understand, we have to look at this as g of negative. In the event we have g of 0.1 minus tau, g of negative tau minus 0.1. So g of tau minus 0.1 would be this g graph moved to the right by this thing, and then you flip it over, and so that's what causes this to move to the right. I didn't explain that well. Yeah, please bear with me. That is right. I thought about it. I had a perfect idea of what the hell I was saying. Right now, I don't. Okay, 0.1. Okay, let me move it to 0.1. Okay, what is it that apparently we need to do? This blue rectangle has scooted to the right by 0.1 units. Now, f of tau times g of t minus tau is what we need to do. That means the blue rectangle times the brown rectangle in the overlapped area. So that would be 2 times 3, on the interval 0 to 1. So that is 6. So that's why you see a rectangle of the size 6, of height 6 and width 0.1. What exactly does that represent, that red rectangle represent? It represents f of tau times g of 0.1 minus tau. Okay, so that's what it represents. Now, what does the integral represent? The integral means the area under this curve. The area under the curve is easy to compute because it's a pure rectangle. So the width is 6, the height is 6 and the width is 0.1. So the area is 6 times 0.1 is 0.6. So you notice there is a little itty bitty point A here. Let me see if I can increase the font size. Yeah, I like that better. Okay, so this little bit point A has coordinates of 0.1 and 0.6. So that is the value of your convolution at t equal to 0.1. Okay, so if we keep scooting this more and more to the right, so we have the same height of the red rectangle because you are constantly multiplying 2 times 3, but the width is changing. As a result, the area of the red rectangle itself is increasing, right? So you notice how that is. And if we scoot past this 1, right now t happens to be 1.09, I make it 1.1. So the overlap, the area is now reduced, right? There is this part of the brown graph, the brown rectangle is not overlapping with the blue one. So the convolution of 2 times 3, ladies and gentlemen, looks like this triangle. It's a triangle whose base is 2 units and it's an isosceles triangle with a height of 6. Cool. So this is a physical or visual representation of a convolution of 2 and 3. Let me see if I can show you one more or two more maybe. How do you convolve t and cosine t? One property of these convolutions is f of t convolved with g of t is the same as g of t convolved with f of t. So I could have switched t and cosine t. So as you can see, I have a cosine tau. Strictly speaking, I should have had t times cosine of t minus tau, but since convolution is commutative, I can switch. Okay, when t equals 0, we have a negative tau. Negative tau is, think of as a negative x, which is what you are seeing. That's negative tau. And cosine of tau is this blue. Now, let's do the same thing as we did before. If we increase time, then we are getting f times g. F times g, that means t minus tau times this cosine tau. So that graph looks like this. And we need to compute the area under that graph. And the area under the graph is what you're seeing as a equals 1.97. So this black that you are seeing is the convolutions value. It's being computed at different time intervals. At t equal to 0, t equals 0.1, 0.2, 0.3, and so on like that. Okay, and it's progressively being calculated as you see here. And when you look at that, that's a graph that just is like a sine graph shifted up. Okay, so this is what convolution actually means. Let me pick one final example. Our favorite, the very first one that we had a closed form solution of, t convolved with t. We already know that it should be tau cube over 6. So we have a tau graph and as t minus tau graph here, this one, and so let her rip. Okay, let me pause there for a second and see what I mean by that. What is that upside down parabola? What is that upside down parabola? Would you agree that is nothing but tau times, in this particular case t happens to be 3, so that is the graph of tau times 3 minus tau. Tau times 3 minus tau. Tau times 3 minus tau, x times 3 minus x is 3x minus x squared. That's a parabola. But there's something else we know. If we have tau times 3 minus tau or x times 3 minus x, the roots are 0 and 3, meaning the zeros of that polynomial are 0 and 3. Is that what we see here? Notice how this curve, the parabola, is cutting it at 0 and at 3. Yep. So this is basically the graph of the parabola is nothing but the x times or tau times t minus tau graph. And we need to figure out the area under the curve, and that tells you what the convolution is at that particular time t. And this a value that you see at this point, which turns out to be 4.5, that is the convolution at this particular value of t. And I can keep increasing t, and this is what you notice. If we were to fit this curve, let me see if I can go back and demonstrate something. Let me go to a t value of 3. When t equals 3, a equals 4.5. Okay. But we thought the convolution was tau cube over 6. Right? We found a closed form solution. We found the convolution t cube over 6. Is this value equal to t cube over 6? 3 cube over 6? 3 cube is 27 divided by 6 is in fact 6 goes into 27 4 times, leaves a remainder of 3, so 4.5. Yep. So what we got closed form completely perfectly matches with what we are getting here. So this is convolution, folks. Now I need to show you one other interesting concept. Mathematicians probably don't care, but since we are engineers, I think we care. I'm done with this slide. Why? What is convolution? Why do we use this convolution and all that? Let me address that. Back in high school, whenever you first got exposed to functions, your teacher must have said something like, hey, boys and girls, a function f is nothing but like a machine, you know. You give it an input x, it gives out only exactly one output. Same input, always the same output for a given function. And only one output, right? And what is that output? F of x, they say. Cool. Now they give you a whole bunch of examples. What if my function f of x is defined as x squared, and if I give 3 as an input, what happens? And you all say, that's 3 squared, 9. And yeah, you are a genius, right? Then what happens? The teacher now says, aha, now that you understand this, what if I did this? That is, I give x as an input to a function f and I get output f of x. But this time, I give that f of x as an input to another function called g. What would the output be? And you go g of f of x, which is what the composition of functions is. Yes. So the output is g of f of x. Cool. So the thing is, does it always work like that? Do all systems behave exactly like this? And the answer is, nah, they don't have to behave like that. For example, there are certain systems to which when you give a unit impulse, delta of t, okay, that's the input, unit impulse. What in the world is a unit impulse? Impulse, let me, instead of giving you a mathematical definition of an impulse, let me just illustrate impulse with a physical quant-ish thing. Like hitting a baseball with a baseball bat, or hitting a drum with a drumstick, or plucking a guitar. What you're doing is you're applying a force for a very short period of time. Applying a force is different from applying a force for only a short period of time. When you apply a force for a short period of time, that's what's called an impulse. Okay, it's like a pulse, just a vertical line. Since mathematicians do not call vertical lines as functions, I'm hesitant to define it like that. But for practical purposes, if you want to see bloop, like hitting a drum with a drumstick, think of it that way, right? So there are some systems to which you apply a unit impulse like this. Then guess what happens? Even though you applied a force for a very short period of time, the output need not be short-lived like that. The output could live much longer. Again, let me go to the drum example. If you strike a drum with a drumstick, that's all you did. But the response of the drum is elaborate. It lasts for a long time. I'm going to make a fool of myself now by trying to imitate a sound. Trying to imitate a drum sound. Boom! Right? So it goes on for a while. And that means it looks like some function of t. It may not be exactly like this. In fact, it should have had a big amplitude in the beginning and then die down. Whatever, some function of t, right? And because this system produces an output of f of t upon a unit impulse as an input, let me repeat that. Because this system's output is f of t, when a unit impulse delta of t is given to it, we will call this system as f. All right? Next, well, let's ask a similar question as we did in the previous case. That is, hey, what happens if you were to give this output f of t to another similar system called g? Why do we call the system as g? Well, we do because if we were to give a unit impulse as an input to this one, it would have produced an output called g of t. That's why we are calling it as system g. Now, what would be the output? No, it will not be g of f of t. In some systems, what you get as an output is, believe it or not, f of t convolved with g of t. That same convolution that we are talking about. And in control systems, this is the kind of stuff that you will constantly be seeing. You will have some input given to one system that comes out as an output, goes into a second system, and that in turn is given as an output to a third system. There could be a whole bunch of things in series, and in fact sometimes you connect them in parallel to get a feedback and all that stuff. So there would be a whole bunch of systems like this that are connected in a network. And we would be interested in finding the output of such a system. Oh, output is piece of cake. You just convolve. Yeah, convolution is a pain. We needed to integrate that stupid thing. And if you are talking about convolving more than two functions, you got to evaluate the integral of something, again another integral of what you get, and an integral, a whole bunch of integrals you need to compute. Right? That's where Laplace transform comes to rescue. But before I move on, I want you to understand why it is that we need convolution. Here is the idea. Some systems generate an output equal to f of t convolved with g of t. Okay? All right. With that, let's go to convolution theorem. Laplace of f convolved with g is nothing but Laplace of f of t times Laplace of g of t. How convenient. We do not have to convolve and do all that integral stuff. We can simply multiply f of s and g of s. So what was convolution in time domain is multiplication in s domain. Multiplying functions is infinitely easier than evaluating the integral, and that's the whole idea. Okay, so okay. Now, let me ask you. Can you figure out what Laplace of integral 0 to t f of tau d tau ought to be? I'm asking you to look at this particular result over here. Laplace of integral 0 to t f of tau g of t minus tau d tau is f of s g of s, f of s times g of s, which came right from this guy. The definition of f convolved with g is this integral, and Laplace of f convolved with g is f of s times g of s. That's what we wrote here. Cool. Now, would you be clever and tell me how to evaluate Laplace of integral 0 to t of just f of tau? Any ideas? Check this out. What if I were to think of, oh, okay, g of t minus tau is just 1. What would this reduce to? Oh, integral 0 to t f of tau d tau. Oh, okay. There we go. G of t minus tau is just 1. On the right hand side, what do we have? We have g of s. That means we need to take the Laplace of g of t. We know g of t minus tau is 1. Can we figure out g of t so that we can figure out g of s? What do you think g of t is if g of t minus tau is 1? Constant function. So g of t is also 1. Oh, okay. What is g of s then? If g of t is 1, Laplace of 1 is what? 1 over s. Cool. So this is nothing but f of s over s. End of the story. F of s times 1 over s, which is f of s over s. Look at how clever that is. Okay. All right. I have a few problems that I solved. Is this an insult of your intelligence if I were to solve problems like this? What does it look like? Does it look like Laplace of integral 0 to t f of tau d tau? Right? What is f of tau? Cosine tau. Can we figure out f of s? We need to figure out f of t in order to find f of s. If f of tau is cosine tau, f of t is cosine t. F of s is Laplace of cosine t. Laplace of cosine t is s over s squared plus 1. Oh, s over s squared plus 1. We need to divide that by s. End of the story. Oh, by the way, what? I didn't simplify this. That's just 1 over s squared plus 1. Right? 1 over s squared plus 1. Wait. Did Laplace of integral 0 to t cosine tau d tau turn out to be 1 over s squared minus 1, 1 over s squared plus 1? Does it make any sense? You bet it does. What's integral of cosine tau d tau? Sine tau. Evaluate that from 0 to t, you get sine t. So basically this integral reduces to just sine t. What is Laplace of sine t? 1 over s squared plus 1. So is this any surprise that this ended up being 1 over s squared plus 1? No, that's the idea. Cool? What about this one? What does it look like? Does it look like this integral, this Laplace of 0 to t f of tau d tau? Or does it look like f of tau g of t minus tau d tau? Notice there is no t minus tau. So you cannot look at it as f of tau g of t minus tau. It is in fact f of tau. What is f of tau though? This whole thing, the product, tau times cosine tau. Well, according to this result, what should we do? Take the Laplace of that t cosine t and divide that by s. As simple as that. Let me repeat that. To find this one, we will look at this as this case, Laplace of integral 0 to t f of tau d tau, with f of tau being tau cosine tau, which means f of t is t cosine t. So the answer should be Laplace of t cosine t, which corresponds to this f of s, over s. That's what I have. Now, the question is, do we know how to find Laplace of t cosine t? Right? Going back to the previous section, if you did all the problems there, you should immediately recognize that Laplace of t cosine t is -1 d ds of Laplace of cosine t. So we have 1 over s dds. Did I go? -1. I should have had a -1 in front of this. Okay. And so just took the derivative of it. I'll say negative here. 1 over, I'll stick a negative in front. Okay. So that's it. -1 over s, or I could have switched this to s square minus 1 over s times s square plus 1, the quantity square. Okay, how about this? How should we look at this as? Would you agree again we should look at this as Laplace of t times some f of t, which means negative dds of Laplace of this integral. Check that out. We should look at this as t times some f of t. That f of t happens to be this whole integral. So negative 1 over negative 1 to the n. What an idiot I am. I do have the negative sign here. I don't know why I forgot to put negative in the previous one. Sorry about that, guys. Negative dds of Laplace of integral 0 to t tau e to the negative tau d tau. So, how do we find this? Kind of like how we found the Laplace of tau cosine tau. It looks pretty similar to me. And that is Laplace of this integral is 1 over s Laplace of t e to the negative t. And to evaluate Laplace of t e to the negative t itself, we have a couple of ways of doing it. That is, think of this as Laplace of e to the negative, let me repeat that. Think of this as Laplace of e to the negative at f of t. So that means we'd be applying a shift of s shifted by s plus 1. And all we need to do is take the Laplace of t, which is 1 over s square, and we apply the shift. Notice we need to apply the shift only to this 1 over s square. That does not carry to this 1 over s. Okay, please remember that. And so we have negative dds of 1 over s times 1 over s plus 1 square. And the next thing we do is just simply take the derivative, quotient rule, and simplify, and you get this. Cool. All right. What about Laplace of t square convolved with t to the 4? Oh, this is a long problem. This is going to be ridiculously long. Okay. What? Yep. Laplace of f of t convolved with g of t is Laplace of f of t times Laplace of g of t, and that's what I did. Laplace of t square is 2 over s cube. Laplace of t to the 4 is 4 factorial over s to the 4 plus 1. And so we got this, and we're done. Look at how simple convolution becomes in S domain. You just simply multiply. Cool. If you were to find the inverse Laplace transform of this, you will actually get the convolution of t squared times t to the 4. Right? That's the idea, folks.